Hi there, welcome to another presentation on elements of matrices. Our emphasis today will be to recap the notion of a vector space, but we're going to specially look at linear combination, linear independence, and linear dependency, and also define the concept of a basis of a vector space. Now, remember the concept of vector space was defined as follows. Now is a set whose elements are called vectors and satisfies the following axioms or rules, whatever I call it. So, like I've said, today we need to look at a little bit more on linear dependence. So we'll start this way. Let's say we've got a subset of a vector space. Let's say subset S of a vector space V, and this S consists of vectors x1, x2, and xn. And then let's say we've got a vector z, which is in V, such that z is equals to alpha 1 x1 plus alpha 2 x2 plus alpha n xn, where alpha I from 1 to n are scalars. In this case, our scalars are actually real numbers. So in this case, you can say real numbers. So if z is a vector which is result in combining these n vectors multiplied by the scalars alpha n, we will say that z is a linear combination of the xi's in S. Now, we can see that, for example, in R2, we've got the following vectors: 1, 0, and 0, 1. We can actually show that with these vectors, let's name them E1, and this one E2. With these vectors, we can show that any vector x, y in R2 is actually a linear combination of these two. In other words, we can find the numbers alpha multiplied by 1, 0 plus beta multiplied by 0, 1 equals to any vector xy in R2. In other words, any vector of R2 can be produced by doing a linear combination of these two. And then such a set in a vector space. Let's say we've got a set B equals to x1, x1, x2, up to xn. So if in a vector space V, we've got a subset B such that all the vectors in V can be written as a linear combination of these vectors. Now, as say, like in this case, Z is in V, and it's just that any Z in V is a linear combination of these vectors. Then we'll call this B a basis of the vector space B. So in vector space V. So we shall say B is a basis of a vector space V if every Z in V is a linear combination of the elements of the subset B. So in other words, pick any V in V, little v in V, then you can find the scalars such that V is equals to, let's say, beta 1 x1 plus beta 2 x2 plus dash 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 beta n xn. Actually, it can happen that some of these coefficients can be 0. That's not a problem. But what is important is that any member of V, vector space V, is produced by making a linear combination of the elements of the basis of the vector space. So coming back to what we have here, we've got a B equals to 1, 0, and 0, 1. This is a subset of R2, and we've already indicated that we can show that any vector in R2 is a linear combination of these two vectors. Let's take an example. Say given vector 2, 3 in R2, and we've got B being 1, 0, 0, 1. We can show that exist scalars alpha 1, alpha 2 in R, such that alpha 1 by 1, 0, start by 1, 0, plus alpha 2 by 0, 1 is equals to 2, 3. So if we can find these two numbers such that we can produce the vector 2, 2, 3 from this, then we can see that 2 is a linear combination of those three. But this happens with any vector in R2, it is possible to find that. For this particular case, what we have here, we will now have a system of equation, an equivalent system of equation, which is alpha 1 plus 0, alpha 2 equals to 2, and here we've got 0, alpha 1 plus alpha 2 equals to 3. This is the equation 1 and the equation 2. Now it is clear from the two equations that we get alpha 1 equals to 2 and alpha 2 equals to 3. So if we choose our alpha 1s, or alpha 1 and alpha 2 this way, we can actually produce this vector. In other words, this vector is a linear combination of these two column vectors. And any other vector in R2, so this is R2 here, is a linear combination of that. And this, such a basis is more or less a natural kind of base for R2, and it's usually called a canonical basis of R2. Now, following exactly similar argument, we can also show that the set of vectors B, let's say here B3 equals to 1, 0, 0, 0, 1, 0, and 0, 0, 1 subset of R3 is a canonical base for the vector space R3. So in other words, a basis, be it a canonical base or any other basis, which is it is possible to find another base which is different from a canonical base. A base will always be that set from which you can produce any vector in the vector space. So again, what we can see also now, coming to what we discussed, is that the linear independence and the linear dependence. As you can see here, 2, 3 is a linear combination of the vector. But at the same time, if we look at the vectors 1, 0, and 0, 1, we should be able to test and show that these vectors are actually linear independent. This set is linear independent. So what you can do is simply multiply this by alpha 1, 0 plus beta 0, 1 equals to 0 vector in R2, and you can immediately show that this actually leads us to the fact that alpha is equal to beta, and meaning that confirming that these vectors are linear independent. So in other words, a basis of a vector space consists of linear independent vectors. So now let's just do one more example on linear dependence. Say example here. Let's say the vectors A equals to -1, 0, 1. The B equals to 0, 1, 0. And this -2, 1, 1. Let's call this one C. So first of all, let's check if this set of vectors is linear independent or linear dependent. So the first step, what we must do, let's say right here, our initial step will be to express the zero vector. In this case, we're talking about the zero vector in R3 as a linear combination of these vectors. So what do you mean there? We've got, say, alpha multiplied by -1, 0, 1 plus beta multiplied by 0, 1, 0 multiplied by plus lambda multiplied by 2, 1, 1 vector equals to 0, 0, 0, our zero vector in R3. Now, we can then take this to our usual system of equation as minus alpha plus 0 beta minus 2 lambda minus 2 lambda equal to 0, 0 alpha plus beta plus lambda equal to 0. Then alpha plus 0 beta plus lambda equals to 0. So we've got equation 1 there, equation 2, and equation 3. So to conclude that these vectors are linear independent, we should establish that alpha, beta, and lambda are all equal to 0. Otherwise, then we conclude that the vectors are linear dependent. So in this case, now we can see from equation 3, let's say from From 3, we have that alpha is equal to minus lambda. Then also we've got that from our equation 2, we have that beta is equal to minus lambda. Now, so in this case, we've got that alpha is equals to beta is equals to minus lambda. Now, substituting in equation 1, we can conclude that these three are equal to 0. So we can now say, therefore, the vectors A, B, and C are linear independent. So that is how we test. Otherwise, if at least one of these scalars different from 0, then we conclude that the vectors are linear dependent. So I hope at this stage the concept of linear dependence and linear independence is becoming clearer and clearer. And we'll talk about this again when we're dealing with eigenvalues and eigenvectors, especially when we're talking about eigenvectors. We'll observe that eigenvectors are actually a set of vectors which are linear independent. Then I think we need one more example. At this point, say we're given a set of vectors S, which is 5, 8, 2, 4, 5, 1, 1, 3, 1, a subset of our vector space R3. In this case, we need to check linear dependence. Now, as we need to check whether the set of vectors is linear independent or linear dependent. Now, we set up our equation, let's say alpha 1 multiplied by 5, 8, 2 plus alpha 2, 4, 5, 1 plus alpha 3, 1, 3, 1. In this case, we're expressing the 0 vector in R3 as a linear combination of the vectors given. So to determine whether this set is linear independent, it means that we must establish that alpha 1, alpha 2, and alpha 3 are all equal and equal to 0. Otherwise, we'll say that the set is linear dependent. At this point, I think it's important to explain that when we are given, let's say, a set of vectors, like 3 vectors like this, and the set result to be linear dependent, it would actually mean that one of the vectors is a linear combination of the other 2. So let's now get our equivalent system of equations, which will be 5 alpha 1 plus 4 alpha 2 plus alpha 3 equals to 0. That's our first equation. And we've got here 8 alpha 1 plus 5 alpha 2 plus 3 alpha 3 equals to 0. Our last equation will be 2 alpha 1 plus alpha 2 plus alpha 3 equals to 0. And this is equation 2 and 3. Now We're going to solve this equation by method of elimination. Okay, then let's start our method of elimination. In this case here, we're going to, let's say, copy our first equation as it is. This will be equation 1. Let's say in this case, we eliminate alpha 1 in the second equation by, say, multiply 8 equation 1 minus 5 equation 2, which will give us 0 here, plus 32 minus 25, that will give us 7 alpha 2 there, and here we'll go to 8 minus 15, which will give us minus 7 alpha 3 equals to 0, and then we've got our equation 2. And the equation 3, we also eliminate alpha 1 here. Let's put a 0 here, which we'll get by saying 2 equation 1 minus 5 equation 3. So here we'll go to 0 to this combination. Then here we're going to get 8 minus 5, which will be 3 alpha 2, and then this point we're going to have 2 minus 5, which will give us minus 3 alpha 3 equals to 0. Now, at this point, we can now decide to work with the last two equations. In this case, we can write here 7 alpha 2 minus 7 alpha 3 equals to 1. And this is our equation 1. And then our equation 2, we decide to eliminate alpha 2 here, which you can do by saying 7 3 equation 2. In this case, I'm talking about equation 2 at this point, minus 7 equation 3, which will give us 0 here and 0 there equals to 0. Sorry, here it's supposed to be equals to 0. Let's correct this here. This is equals to 0. Then from this equation 1, we get that 7 alpha 2 is equal to 7 alpha 3, which is equivalent to saying alpha 2 is equals to alpha 3. Now we can substitute alpha 2 or alpha 3 in equation 1. Here what we're going to get is 5 alpha 1 plus, if we take alpha 2, this will be 4 alpha 2, which will give us 5 alpha 2 equals to 0, which implies that alpha 1 is equal to minus alpha 2. Now in these two parts, here and there, we can see that our alpha 3 depends on alpha 2 and the alpha 1 depends on alpha 2. So, which means in that case, we can freely choose alpha 2. Let's say, let alpha 2 be equals to 1. Then we're going to have our alpha 1 equals to minus 1, and alpha 3, which is equal to alpha 2, is equals to 1. As you can see, all the alpha i's are not equal to 0. In this case, I is equals to 1, 2, and 3. So, which means that the set which we're given above here is linear dependent. So, we write here that therefore S is linear dependent. So, actually, what we can do, we can at the same time check which of the vectors is a linear combination, let's say, of the other two. Now, the vectors given are actually 5, 8, 2, and 4, 5, 1, 4, 5, 1, and the last vector is 1, 3, 1, 1, 3, 1. Now, if you now look closely, I think you can see that 1 times 1, 3, 1 plus 1 times 4, 5, 1 is actually equals to 5, 1 times 3, 1 times 5 gives us 8, and then 1 times 1 plus 1 times 1 would give us 2, which means actually the first vector given there is a linear combination of the other two. So that's what actually linear dependence means. Now, at this point, I think it's enough of examples. Now what you need to do, you need to do some bit of practice, and for that, I'll give you the following homework. In this case, your task is to verify or to check if each given set is linear dependent or linear independent. And in the case the set is linear dependent, I think I would encourage you also to check which of the vectors given is a linear combination of the other two. So that's the first set. The next set is V. And then where we put 1, 3, 0, 0, 7, 2, and minus 1, 4, 2, so and our last set is T. We've got 1, 3, 0, 0, 1, 2, minus 1, 4, 2. Right. I repeat, in each case, verify if these sets of vectors are linear dependent or linear independent. In the case the set is linear dependent, please also try to identify one vector which you can express as a linear combination of the other two. So after these examples, you can take some further practice with some exercises in your book or another textbook which is on the same material. And the other thing is, what is important is I can also encourage that given a matrix, let's say a 3 by 3 matrix, you can also take the columns as column vectors, and you can actually do the similar practice of practicing and checking whether the column is given a linear dependent or linear independent vectors. Otherwise, this is what I wanted to add on what we had in the previous lecture. And very important here, I'd like you to be very clear on the concept of what we call linear combination. Linear combination, how to express a vector as a linear combination of others, and also linear dependence stroke independence, and also the concept of a basis. Here you must keep in mind that the basis is actually we can look at it as a foundation of a vector space. In other words, each and every vector in the vector space can be built as a linear combination of the vector of the members of the basis. You just maybe need to identify with what scalar coefficients you need to multiply the vectors in the basis. And my advice is, as you're looking at examples in this presentation, please try to write also, so that you can don't only watch as if you're watching a soapy, but practice as the examples is given. Also write. Then after that, try to do your own further examples independently without looking at the video clips. But when you get stuck, you can go back and relook at the examples and see what you have missed. Otherwise, at this point, thank you for listening. Meet you in the next presentation.